Hello, welcome to Econometrics Melody. In this video, we'll discuss about the parameter estimation, especially the maximum likelihood estimator. For independent events, the joint probability is equal to the product of their individual probability. In other words, the probability mass function or the probability density function of the joint distribution is equal to the product of their individual either probability mass function or probability density function. And for optimization problem, that is either we need to maximize or minimize a given function. First of all, we calculate the first order derivative and we set it to 0 and calculate the value of x. And if the second order derivative is positive, then the value of x is going to minimize the function. And if the second order derivative is negative, then the value of x is going to maximize this function. Now let us create a context for the maximum likelihood estimator. So we are taking a sample from x1 to xn. These are independent random variables, and we know or we assume that these data points or these observations follow certain distribution, but we don't know the parameters defining this function. So as these random variables are independent, making use of the property of independence, we construct a joint distribution, that is the probability mass function in case of discrete random variable and probability density function in case of continuous random variable, and we try to maximize the likelihood of this joint distribution in such a way that it best fits this data. So in other words, we estimate the unknown parameter in such a way that it best fits the distribution for these data points or for the sample. So maximum likelihood estimator, it is also a point estimate. So it helps us to calculate the point estimate, and these are some of the important points related with maximum likelihood estimator. So this is our likelihood function, and we don't know the parameter theta of the joint distribution created out of these data points, and these data points or these random variables, they are independent. So this is equal to either the probability mass function or the probability density function, depending on whether the distribution is discrete or continuous. And making use of independence property, so the joint distribution, we are going to represent it in terms of the product of their individual distribution for each data point. So let us see an example of an optimization. How do we calculate it? Here, y, this is equal to function x equal x squared plus 8x plus 7. And this is a problem of minimization because the graph of this function is a parabola. So we can calculate its minimum point. So how do we operate it? So let us take the first order derivative. So this is equal to, I'm assuming that we know to calculate the derivative. So let us again take the second order derivative. So second order derivative is equivalent to taking the derivative of this first order derivative. So as this value is positive, so this is the case of minimization. Now in order to find the value of x that minimizes this function, so we must set the first order derivative to 0. And if we take it common, we are left with x plus 1. This is equal to x plus 1. So this function for x squared plus 8x plus 7 is minimized by x is equals to minus 1. Now let us take 3 points, x is minus 1 and 1 less than 8 minus 2 and 1 greater than 8 0. And let us calculate the value of the function at these points. This function is minimized at x is equal to minus 1. So the minimum value of y is 3, and anything less or greater than 8, that is greater than 3. So in maximum likelihood estimator, we are going to use this property. We'll calculate the first order derivative of our likelihood function, and then we'll set it to 0 and we'll calculate the value of the unknown parameter. And that will maximize the likelihood of the assumed distribution best representing or best fitting the samples. Now let us see 2 examples of a maximum likelihood estimator. So in our first example, we take a sample from x1 all the way to xn, and they are independent random variables, and we assume that these data points, they follow a Bernoulli distribution. Now we need to estimate the probability of success. The Bernoulli distribution or Bernoulli random variables, they are the discrete random variable. That is why we have a probability mass function. So let us create the joint probability mass function. This is our likelihood function. And as they are independent random variables, we can write them as the product of their individual probability mass function. So the probability mass function for Bernoulli random variable is equal to, so this is our probability mass function, and let us check. So what is the probability of success? So the probability of success is P. Similarly, let us calculate what is the probability of getting failure. So the probability of getting failure is 1 minus P. So this is the probability mass function for the Bernoulli random variable. Now in this probability mass function, let us substitute each data points from x1 to xn in this function and take the product of it. So this is equal to, and we take the product from x1 all the way to xn. Let us collect the like terms together into, so this represents p to the power from x1 to xn, and this represents 1 minus p to the power 1 minus from x1 to xn. Now let us apply the laws of index. So this is equal to probability of the sum. If the base are same, then in case of multiplication, we add the index into 1 minus p to the power 1 minus x1, and we add all the way to 1 minus xn. So this is equal to, let us apply the sigma notation. We are summing all the x from x1 to xn. Let's operate the summation of 1. This should give us n minus and then summation x. So for our convenience, let me represent this likelihood function by y. Now let us take log on the both sides. Therefore log y, this is equal to, and let us apply the property of log. So log a into b is equal to log a plus log b. Now let us apply another property, log a to the power y. This can be written as y log a. So this is again equal to, now to maximize or to optimize this likelihood function, we take the derivative, first order derivative, and we set it to 0. Therefore derivative of this with respect to the unknown parameter, here it is p, this is equal to summation of x. Here we have p, and another property related with log. So derivative of log x with respect to x, this is equal to 1 by x. Let us apply this property. We get 1 by p plus, we don't have p over here, so they are something like a constant when we compare it with p, and here we are going to apply the chain rule. So first of all, we consider 1 minus p is x. So derivative of log x is equal to 1 by x 1 minus p, and further we are taking derivative of this term with respect to p. So we'll get, so we need to further multiply this term by minus 1, plus minus minus. So this is our first order derivative of our likelihood function. Now we need to set this to 0. So what do we get? We get summation x by p. This is equal to n minus summation x divided by 1 minus p. Now let us arrange it according to our requirements. Simply we have changed their position, and let us separate them, or and now let us apply the axiom of equality. So we have minus 1 on the both sides, and if we apply the invertendo, so p divided by 1 should be equal to summation x divided by n. Therefore this is our maximum likelihood estimator. Estimate the value of p is the average of x, and is in Bernoulli random variable x takes the value either 1 or 0. So summation x, this represents the sum of success only. So the sum of success divided by the total observation, this is equal to the proportion of success. If the sample followed a Bernoulli distribution, then the best estimate for the probability of success, this is equal to the proportion of the success. So this is our MLE estimate. Now let us see another example. For another example, let us again take our sample x1 all the way to xn. Our sample size is n, and each of the xi, they are independent and Poisson random variable. And Poisson random variables, they are also discrete random variables. So we have a probability mass function. So let us define the probability mass function of the Poisson random variable age. So we calculate this function for each of the observations from x1 all the way to xn, and as these are the independent random variables, so we construct their joint probability distribution or joint probability mass function. That is our likelihood function. Here we want to calculate lambda. The parameter lambda is unknown, and we want to calculate the lambda in such a way that the likelihood of this distribution is maximized, meaning thereby this distribution best fits the sample data. We are going to find that value of lambda. As they are independent, we can express this as. Now for each observation x1 to xn, let us calculate the value of this function and we take the product of it. For our convenience, let us denote this likelihood function by y. So this is equal to. Now let us collect the like terms together. So we calculated this for n number of observations into for n number of observations, and we divide this by x1 factorial all the way to xn factorial. So here we have multiplied e to the power minus lambda n number of times. So this is equal to e to the power minus lambda and n into lambda, and if we apply the laws of index, then for when the base is same, then in case of multiplication we add the index. So this is equal to divided by into lambda to the power summation of x. We are adding all the x, and we are going to apply this property log e to the power x. This is equal to x log e, x into 1. Natural logarithm of e is equal to 1 because the natural logarithm, it has this Euler number is its base. So therefore log e to the power x, this is simply x. Similarly, log a into b divided by c, this is equal to log a plus log b minus log c. For multiplication we add, and for division we subtract. We'll use this property as well. Now let us take the natural logarithm on both the sides and apply the property. Therefore log y is equal to, this is equivalent to log ab divided by c. So this is equal to log a plus log b minus log c, and log a to the power x is equal to x log a. Let us apply that property. So log e to the power x is equal to x only. We have seen it over here. And plus log a to the power x is equal to x log a minus. Now in order to maximize log likelihood function, let us take the first order derivative of this with respect to lambda, because we are going to estimate lambda. We have lambda over here, so this is equal to minus n, plus we have lambda over here, so this is summation x. Derivative of log x, this is equal to 1 by x, so this is equal to 1 by lambda minus, and here we don't have any lambda, so this entire term is going to be 0. So this is equal to minus n plus summation x divided by lambda. Now to maximize, we need to set our first order derivative to 0. So if this is 0, then we have summation x divided by lambda. This should be equal to plus n. If we operate it cross multiplication, then we get lambda is equal to summation x divided by n. This is again an average sample mean. The lambda, when estimated using maximum likelihood estimate, this is equal to the sample mean. Now let us summarize our results. We have our sample and it contains n number of observations, and each of them are the random variables. They are independent random variables, and if our sample it follows the Bernoulli distribution and we want to find p such that this distribution best represents our data set, then according to maximum likelihood estimate, the value of p is attained by summation of x divided by n, where summation of x is the sum of all the successful observations and we divide it by the total observations. So this gives us the proportion of success. On the other hand, if we think that our sample data set follows a Poisson distribution and we want to find the value of lambda such that these observations best fit the Poisson distribution, then in that case, according to maximum likelihood estimator, mean of the sample maximizes the likelihood of the distribution representing our sample observations. So we have sample data points, and we think that a certain distribution best fits this data, but we don't know the parameter of that distribution. So maximum likelihood estimator, it restructures this distribution by calculating the unknown parameter in such a way that the likelihood of this distribution representing this data is maximized. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.